Good morning to everybody. So we'll wait for a few more students to join before starting on today's session. Okay, we'll start today's session with an extended discussion on the particular analytical tool available for defining a certain level of certificability outcome in the avionics system. Okay, so all of this is connected with the broader topic that defines the performance of avionics systems, which are called as the utilities of the avionics system. So one of them is the certificability, right? So the final failure modes and effects analysis is the specific analytical tool that is invoked in order to rate the performance of the avionics system while it is still in the concept and design phase. Okay, so it is effectively a bottom-up approach. It is a sort of developmental or constructive attribute that is associated with this invoking of the FMEA. Okay, you also have a parallel opposingly directed analytical tool, which is the FTA, that is considered more in the manner of a failure analysis, while here it is, even while associated with failure analysis, applied in a manner where potential failures, which means those that are likely or forecast in the future, can be identified right away and rectified even before the product comes into existence. Okay, so in effect, avionics systems can be identified in several domains in which they are considered functional. One is as a product, okay, which means you have a physical representation or a hardware level realization of it with the attended software that is running in an embedded manner. Okay, so you may have a process identified also as part of an avionics system, which means that it has been deployed in a manner where there is a certain utilization identified for it. Okay, and it is in its functional mode. So it is a avionics system as a process. You also have an attribute of a service identified with the avionics system, wherein it clearly offers some benefits as an outcome of its deployment. So you have either a product, a process, or a service, all of which constitute the case for an avionics system that either is in a phase where it is completely deployed or in a phase where it is being designed and developed. Okay. So FMEA, when is it more appropriate to apply this particular analytical tool called the failure modes and effects analysis tool? Okay. So there are several contexts The first one is when the process, product, or service is being designed or is being redesigned, considering that there are first levels of drawbacks that some of the attributes are clearly showing up during its operational phase. You go back and do a redesigning of the entire avionics system. Okay, and this primarily happens when there is something called as the quality function deployment. Okay, so it's a management term that is primarily used as part of the design and developmental exercise, wherein you will need to bring in some level of verifiable attribute to the overall process. Okay, so you have what is called as a quality function deployment exercise. So this QFD is primarily after which the FMEA is invoked. Okay, so the QFD, what is it? So quality function deployment is a method of transforming a set of user demands into design quality. So the user may have certain specifications, as we had seen in one of the earlier discussions related to the Lecture-10 aircraft, wherein there is a certain expectation from the user and there is a practical realization. So one and the other are put across each other in order to see how much there had been a match in several criteria that have been identified by the user. Okay, so effectively there is a transformation that is defined that converts the demands into design quality, so that it is possible to deploy the functions that define quality and deploy the methods for achieving the design quality into the various subsystems and components. And as an outcome of all this, to specify the elements of the manufacturing process. So from there onwards, during the fabrication and large-scale manufacturing exercise, you have a possibility to identify a one-to-one scheme of enabling transformation from the demand into the typical product design quality aspects as well. So this technique is also identified as part of an ISO 9000 series of standards and rating. And this primarily focuses on customer satisfaction more than anything else. So the user demands and the emphasis in providing for those demands in the development of a particular avionics system are primarily the criterion that drives the ISO specifications scheme. Okay, and quality function deployment is essentially a tool or a set of transformation activities that bring about a conversion from demand into realization of the particular avionics system. All right, so it is after this is complete that you will invoke the failure modes and effects analysis analytical tool, which may be either in the context of a design or as a redesign exercise. So the second context is when an existing product, process, or avionics service is being applied in a totally new manner that has never been envisaged before. Okay, so there may be a totally new domain in which the existing avionics system has got a functionality identified with it, which has been realized during the course of operation with the particular avionics system. So if that is indeed found to be true, you will again have to investigate based on FMEA where there is a chance for a failure in its new role. The third one is before developing what is called as a control plan for a new or a modified process. Okay, so now let's come to the case of what is called as a control plan. So it is a intensive level of detail that goes into this document called the control plan that sets the limits within which the process should operate. So this tool is a big list that specifies the process activities and then states the variables or risks that will affect these various processes, as well as the specifications that have to be followed in applying the avionics systems or solution to the particular process. So if you indeed have a case where there is a new or a modified process identified in which the avionics system can be deployed for confident utilization, you will need to primarily develop what is called as a control plan, and FMEA is applied before the actual control plan is being developed. Okay, so that now the control plan with the inferences obtained from the FMEA can be used for the new or the modified process. The next possibility for use of FMEA is when the improvement goals are planned in an existing process, product, or service. So it's not like an incidental finding out of a new role for the avionics system. If this avionics system has to be repurposed, which means it can be used for a different one, and there is an investigation that is conducted in order to find out this repurposed role. Such improved goals are also identified as a part of the planning of the avionics system's utilization in its existing form into an improved set of goals which need to be tackled with it. Okay, so then FMEA has to be again invoked. The following one has to do with the analysis of failures in the existing product, process, or service. Evidently, it is a backward looking or a so-called detective approach in which FMEA can also be deployed, while fundamentally it is a constructive attribute. So it is used predominantly in the design and development phase. It can also be used as part of the failure analysis in its actual form, okay, wherein your event and the cause can now be reversed in terms of how they are approached. So it is a top-down approach that you will be adapting there. Next is FMEA can also be used periodically throughout the life cycle of the entire process, product, or service, so that you have a possibility to calibrate the overall performance of the avionics system and keep it in its optimum functional window. Okay, so it is neither falling back in terms of performance, nor is it likely to exceed its envelope of performance. So that kind of a optimum performance limit range can also be defined by periodically subjecting FMEA to a particular avionics product, process, or service. All right, so now let's look at the methods that are available to give a precise quantified numerical value to the outcome of deploying the analytical tool called the FMEA. Okay, so it is based on certain parameters which have to be all in place to start with before the eventual quantification of the FMEA can be done. Okay, so what's the purpose of giving a number as an outcome of the invoking of FMEA is because based on that, you can clearly assign a certain priority, okay, as to which avionics system or subsystem needs to be attended to earlier than the other one. So that ranking list can be generated by primarily coming up with a scheme for the ranking itself, okay. So here you have what is called as a risk priority number, RPN, that is identified. So it is a product of three separate parameters. One is the parameter called the severity rating. The other one is the occurrence rating. And the third one is the detection rating. So what is the level of impact that has been suffered by the avionics system? So the so-called severity, the frequency with which a particular problem is cropping up. This can, mind you, be done even earlier to the actual availability of the product in its physical form itself. Okay, so during the design phase, I mean. So the number of times it can potentially suffer a failure. And the third one is the abilities to detect such failures in the first place. Okay, so even before they show up or after they have shown up, so you can have a preventive or a corrective aspect taken care of at that stage. So that kind of a detection rating is also given. So severity rating, occurrence rating, and detection rating. And the risk priority number is a product of all of these three. And it is typically given on a scale of 1 to 10, where on the scales which has a side 1, it is considered as an insignificant issue which needn't be immediately attended to, while a scale of 10 means it is a catastrophic possibility which needs to be immediately rectified. Okay, so that priority assignment is primarily enabled with the so-called quantification of FMEA using the parameter called the risk priority number. In addition to this, you also have another parameter called the criticality. So it is just two terms that go into this, the severity and the occurrence. Okay, the product of the severity and the occurrence gives the criticality factor. And this again can be used as a secondary means for assigning priority to the various levels of attempt that have to be made to rectify a certain problem in an avionics system. So these numbers effectively provide a guidance for ranking the potential failures in the order where they have to be addressed. Okay, let's look at this particular understanding of the nature of either a success or a failure attribute in the avionics system. Okay, where you have two ends and a whole series of shades of gray identified between the two extremities of one corresponding to a product, process, or service that has failed, the other one where it has been a complete unequivocal success. Okay, so depending on which direction is being taken in the form of the analysis across the various stages, you have evidently an inductive and a deductive modeling scheme. So an inductive model considers an initiating event as the first element which can have an undesirable consequence. Subsequent events are identified, which in turn define possible progressions of this initiating event. So if you have a single failure case that can be first defined, which can eventually contribute to a complete failure, you will need to know that. And you also have to know the possibilities by which this failure propagates to the next several sets of events. Possible realizations of the subsequent events are defined, and they are now linked to typical scenarios, which are called as the model scenarios. So the consequence of each scenario is also described as part of the inductive modeling scheme. When you look at the deductive modeling scheme, which is like a reverse process that starts with the causes and works all the way back to the elements, you have an event as first defined for which causes are to be fundamentally resolved. So the event is resolved into its immediate and necessary sufficient causal events. So the event is related to these causal events using appropriate logic parameters, such as the logic gates, connectivity in the form of the flow diagrams, and so on. So this stepwise resolution of the elements and events into immediate causal events proceeds until you reach the basic cause, which is the primary cause for failure. And identification of that would be the culmination or the so-called end brought about to the deductive modeling scheme, in the analysis of failures. So you have inductive models and deductive models which work against each other in terms of the way they are oriented in their approach to either defining a success or a failure case for an avionics system. Right, so let's look at the deductive models now, having seen the FMEA as one tool identified with the constructive or inductive modeling exercise. Okay, so when it comes to the deductive modeling scheme, in terms of a variability, you clearly have an undesirable event which occupies the prime position right up front, and you are going to systematically work your way to the previous stages all the way down to the fundamental attribute. Okay, so that's the plan of the fault tree analysis. It's a systematic deductive process which primarily starts with defining the undesirable event, which is usually a failure of an avionics system or the entire aircraft, if it has to be that. Okay, an entire aircraft is a bunch of various avionics systems that reside within it. So the event is primarily resolved into its immediate causal events. So this ability to resolve, also called as the resolution of the events, is taken in several levels of further refinement, okay, or the intermediate causal events. So you have a possibility to work all the way to the basic causes. Until these are identified, this resolution exercise proceeds on and on. So the resolution of the events continues until the basic causes are identified. After which, because it is called as a tree, you'll need to evidently come up with some sort of a morphological representation of the tree. Okay, so that's where you go for the fault tree scheme. It is a logical diagram. It is constructed and it tries to link the various undesirable events, intermediate attributes, and the basic events by means of a clear branching process, which is the so-called logical event relationships. So the logic diagram is called as the fault tree. It is constructed in a manner where it shows the logic event relationships between the or among the various undesirable events, immediate causes, and the basic causes. Now let's take a look at the benefits of constructing a fault tree as a deductive modeling approach to fault analysis. So the fault tree explicitly shows all the different relationships that are necessary to result in the top event. While constructing such a fault tree, a thorough understanding is obtained of the logic and basic causes that lead to the top event, which is the failure case. Okay, so the so-called undesirable event or the failure case has a complete way of getting defined with the process that goes into understanding the logic and basic causes as the tree is being constructed. So the fault tree is a tangible record, which means that it has a productive outcome for it, which is completely linked with the undesirable event. So you don't really branch it off into an analysis pathway that doesn't lead to anything. So there has to be a tangible outcome for the activity that is being pursued along the fault tree scheme. This fault tree is a systematic analysis of the logic and basic causes that lead all the way to the top event, which is an undesirable event of failure. So the fault tree provides a framework for a thorough and quantitative as well as qualitative evaluation of the failure case or the undesirable event, which is also the top event in a fault tree analysis scheme. So let's look at the elements of the fault tree analysis. Okay. So FTA, in short, for fault tree analysis is a deductive analysis approach for resolving an undesirable event into its causes. FTA is backward-looking analysis. The looking backwards is primarily aimed at the various causes that have led to a particular top-level event, which is a failure event also. It is a specific stepwise logic that is applied in the entire process of fault tree analysis. Specific logic symbols are used in order to illustrate the event relationships. A logic diagram is also constructed showing the event relationship. So with all of these attributes that go into the elements of the FTA analysis, there is a means to portray the overall analysis procedure in a more effective manner. So let's look at the reasoning behind why it has to be carried out in a deductive scheme. While there are a few other methods also available, what are the principal advantages that can be gained out of invoking the FTA as a failure analysis scheme in avionics systems? So why is FTA carried out is because in order to exhaustively identify the cause of the failure, to identify weaknesses in the system, to assign a proposed design in terms of its assessment for reliability and safety, to identify effects due to human errors. That is also one more attribute, although human errors would be also considered as some of the basic events and not intermediate attributes, as we will see during the progress in these discussions. So fault tree also incorporates within its ambit of analysis an element associated with possible failures primarily attributed to the presence of human beings in the avionics system. It also prioritizes contributions and factors that contribute to failure. So that you had in FMEA the possibilities to prioritize using RPN and the criticality, as we saw a little while back. There is also a means available to prioritize the contributors to failure, which means intermediate or basic events. FTA is carried out to identify effective upgrades to an existing system in the similar way I told you about the FMEA, its abilities to be incorporated as part of the redefinition and redeployment or repurposing of an existing solution. You can also come up with means to upgrade an existing system. In order to quantify the failure probability and contributors to such failures, that is again one more role it performs. And FTA also optimizes the test and maintenance procedures because of the level of resources that are required for the testing and the maintenance aspects. Rationalizing the use of such resources is again one more attribute that is identified as part of the fault tree analysis procedure. Let's look at some of the roles of FTA in safety analysis in an avionics system. FTA is used to resolve the causes of system failure. It is used to quantify system failure probability. Okay, so that from there onwards, priority can be assigned to the specific subsystems and modules and components in order to resolve the issue associated with them so that the failure is understood or is avoided. FTA is used to evaluate potential upgrades to a system. It is used to optimize resources in assuring system safety. It is also used to resolve causes associated with a potential incident that can unfold on a future time scale. And FTA is used to model system failures in risk assessments. So that is eventually the developmental aspect of FTA also considered. While principally it is a deductive scheme, it can certainly be used in the context of predicting a case for failure or a particular event from taking place and potentially looking at avenues for avoiding such failures, looking at upgrades in a system, which is a constructive exercise, assessing the risk of failure, which is again an attribute that is useful during the developmental process of an avionics system design. Let's look at what are the thought processes that go into a fault tree analysis process. FTA is fundamentally backward looking. It is deductive. It is a destructive attribute. If you were to consider that the avionics system has already undergone a fair level of deterioration or repair or destruction associated with its malfunctioning. Okay, so it is backward looking. So the starting point is a failure that's in turn resolved into further elements of causative attributes to that failure. Okay, so it is a systematic process that works from the failure all the way to the reason for the failure. Hence, it is a backward looking scheme. So the end result is the starting point of the analysis here. So the end result is then tracked back one step at a time to its intermediate causes. So the relationships of these causes to the various events which are above it are primarily linked using logic symbols. And you are aware of logic symbols such as the AND or gate and so on, which can be used here. So this backward tracing process continues until the basic causes are identified. And FTA systematizes and codifies the entire process. So you have a visual representation of the overall procedure of analysis that was performed in a more systematic manner. So the codifying aspect is effectively in the form of drawing the fault tree itself that connects the various events to the corresponding causative attributes or components or subsystems in the avionics system, collectively speaking, which had led to a potential failure as the first step in the analysis process. Taking the discussion on FTA further on, we'll try to see how it contrasts against various other fault analysis schemes. Okay, so if you look at some of the informal methods for visualizing and depicting fault analysis, an example of which is called as the fishbone analysis. Okay, so it's used very much in quality control and management circles. It effectively consists of drawing an informal diagram called as the fishbone diagram. In effect, it tries to link the various factors that have contributed to a certain top level event, such as a failure case. Okay, so the head of the typical diagram representing a fish skeleton is the problem or the actual outcome itself, and these are linked to various phenomenon that have been causative factors for the eventual failure. Okay, so that indeed constitutes the so-called branches or bones away from the central backbone of the fish bone diagram skeleton representation case. Okay, so the branching depends on the levels required under each classification. So that is a very informal and deductive approach. And compared to that, FTA is certainly a more formal means for obtaining a deductive means of connecting the top level events of failure with the fundamental causative factors for failure. Then you have FTA, which is not at all in any manner resembling the failure modes effective analysis scheme, effects analysis scheme, FMEA, because FMEA assesses different effects of a single basic cause, and it is fundamentally inductive in nature. And FTA is not event tree analysis, which is again a informal inductive approach. In the case of the event tree analysis, the assessment happens in terms of the consequences of giving the particular failure case against the given set of initiating events that have resulted in those consequences. So evidently it is informal inductive, while FTA is a formal deductive exercise. FTA is a formal approach for resolving the basic causes of a given undesirable event. Hence, it is in all cases a very formal and deductive approach that is applied compared to various other schemes that also exist for failure analysis. Now, let's look at the two spheres of defining a product functionality. Okay, one is called the failure domain, the other one is the success domain. And we have FTA here primarily operating in the failure space. So designers or product developers are pursuing a certain line of activity which is towards success. Okay, safety analysts are the kind of engineers who analyze with failure always topmost in their mind. Okay, so this in turn can be resolved into varying degrees of success and failure. Okay, thresholds for failures are certainly identifiable. Failure events can be more readily defined and discretized, which means you can resolve them into further basic reasons for the failure. Failure quantifications are by and large simpler. And one more attribute that has to be there in safety analysts who are also engineers working in the product development or troubleshooting and failure analysis domains, they will need to have what is called as a failure mindset, which will potentially be probing for weaknesses or gaps in technology associated with an avionics system. So the fault tree models are primarily attempted as failure models. A failure model is the failure state of a system or a component associated with the avionics system. Examples of failure modes are a failure to start, which could be associated with an avionics system's inoperability condition, a failure to deploy, or a failure to shut down. Okay, so all of these attributes can be construed as failure modes. Ability to not even make a start, ability to not be in a functional mode even while it has started, and ability to remain in an operational mode while it is required to be shut down. So those are all attributes of failure. Contrasting this case, you have failure mechanisms, which are processes by which these failures occur. Examples of the failure mechanisms are aspects such as corrosion, excessive pressure, and fatigue in physical components. In addition to that, you have various other mechanisms of the software kind, such as intrusion and various other errors, which are unintentional or primarily not defined during the time of development of the software tool. Okay, so in any of these cases, you have possibilities of failure mechanisms showing up as prominent reasons for the failure of the avionics system. A failure mechanism is only included in the failure mode definition when detailed mechanisms are going to be modeled. Okay, so that's when you will notice that there is a contrast between the failure state and failure modes as well as the failure mechanisms. So evidently, you can notice here that on one side of this pair of domains where there is either a failure or a success attributed to the avionics system, you have a tolerable level of failure, anticipated level of failure, which could be either a maximum or a minimum value. Similarly, on the side of the success, you have minimum or anticipated value of success, a minimum accepted success, and a maximum case of the anticipated success, which means it is likely to be successful on a potential basis in future. That is when you anticipate it. Okay, so that can anywhere be from a minimum to a maximum, be it for a failure case or a success case. So the fundamental aspect of the fault tree analysis is that you create a fault tree, which means it's a diagrammatic representation that is always generated as an outcome of this analysis. The fault tree is a logical model of the relationship of the undesirable top event to the fundamental or basic events, which may be one or several. So the top event of the fault tree is the undesirable event itself, like a failure of the avionics system. So the intermediate or the middle level events are also there, which connect the top event to the basic ones. So the bottom level in the fault tree is occupied by the causative attributes or the so-called basic events or the primary events as they are defined. So the logical relationships of the events are primarily depicted in the form of logic symbols and logic gates. So as you can see here, there is the objective in the FTA, which is primarily to define what is called as a failure. Okay, so then that then constitutes what's the top event itself in the fault tree analysis. So from that you have various steps which have to be followed, such as defining the set of ground rules in order to analyze, define what is called as the resolution. We'll be looking at that term also, and define what is the overall ambit or scope of the FTA. Okay, so these three are happening at a single level. Beyond that, you have actually the construction or the drawing of the fault tree. After it is complete, it is subjected to an evaluation. If the evaluation is not very productive or leading to a certain result, you have an iterative scheme which is followed in terms of redefinition of the scope, resolution, and the ground rules, followed by a reconstruct of the fault tree and a subsequent evaluation. So when there is a clear set of events which constitute the primary or basic events, you have a possibility to announce the outcome of the fault tree, which is to present the results and give an interpretation on the overall analysis process. So that's the complete steps that are being illustrated as part of the fault tree analysis. So there are primarily four important steps that can be identified here. First is to define the undesirable event for the analysis. The so-called focus of the FTA is to be right there. Okay, so beyond that, you define the boundary of the analysis scheme. The so-called scope of the FTA is defined at that point. Then you have the definition of the basic causal events that have to be also considered for the analysis. The resolution of the FTA, to what level of detail you'll need to proceed in a systematic step-by-step fashion, so that you can put a complete end to the analysis process at some point in the ongoing phase of analysis using FTA. So that breaking up of the various intermediate steps into further primary or basic causes, and how much level of detail needs to go into the identification of those causes. Okay, so that's called the resolution. Then you define the so-called initial state of the system, which is from where you proceed with in terms of the analysis procedure. So that together constitutes the four important steps that are defining the beginning phase of a fault tree analysis scheme. All right, so for today's session, I'll stop on this slide. If there are any queries, you could get them clarified now. We'll be proceeding with the actual scheme for defining the attributes in a fault tree in terms of its visualization, its construct, and so on in the following session of the course, which is tomorrow during the last slot for the day from 3 p.m. onwards.